Today, I want to explain the p-n junction. If you understand how the p-n junction works, you can understand how a diode works, how the bipolar transistor works, and how the MOSFET transistor works. So let's start by reviewing p-type and n-type silicon. Here I have a lattice of silicon atoms. The circle represents the nucleus of the silicon atom. Now recall that each silicon atom has 4 outer electrons. Now this silicon atom will share electrons with the adjacent atom. Now if I want to take this pure silicon, this intrinsic silicon, and I want to create a p-type material, I can introduce an impurity. And when you introduce an impurity, this is called doping. So in this p side, I want to replace this silicon atom here with a boron atom. And recall that a boron atom, instead of having 4 electrons in the outer shell, it only has 3. So I'm going to remove one of the electrons here. And I'm going to replace that with an X. And this X means that I have a hole, or I have an absence of electrons. And when I have this situation, this silicon lattice is no longer stable. Charge can move around. For example, this electron can move over to this slot. And when that happens, this hole will go away. The electron will jump over here. This electron goes away. And the hole moves over to this location. So when I add this boron atom, the net charge of this region is neutral. And what that means is the amount of positive charge equals the amount of negative charge. Adding this boron atom didn't upset the charge neutrality. Even though it had 1 less electron, it also had 1 less positive proton in the nucleus. So the charge remains in balance. If I want to create an n-type silicon, I can do that by replacing one of these silicon atoms with a phosphorus atom. Now recall that the phosphorus atom has an extra electron. So I'll draw that as a little diagonal line here, showing that this is an extra electron. Now if I apply a voltage across this n-type region, these electrons can move around as a result of applying that voltage. So I want to represent this p-type region and this n-type region with a symbol, because I want to put these regions together and show you how a p-n junction diode works. But I don't want to draw all these little silicon atoms and all these electrons. So let's take this p-type region and let's replace that with an equivalent symbol. And I'm going to just show an atom nucleus, and I'm going to show this little X. This little X is a hole. And this O is a nucleus of the atom. It's very stable in the lattice. It doesn't move around. So this hole is what can move about and cause current flow. Now, in the n-type, I want to represent that by a symbol. So here, I'll represent the nucleus as a circle, and the extra electron is represented as a little a little diagonal line, like an apostrophe. Now I want to take these symbols and explain how a junction diode works. So let me erase this. Now I want to take the p-type region and place it together with an n-type region. So let's say that this is the p-type region. And I'm going to use my symbol. So I have a lattice, a fixed nucleus, and I have a hole, and a hole. And I have the same thing out here. And I have a nucleus, hole, nucleus, hole, nucleus, hole. Now recall that the nucleus is locked into the crystal. It's not going to move around. My charge carriers are these little X's, are the holes. So this is the p-type region with the holes. And now let's add to the right an n-type region. Now I'm going to use my symbol again. So this is a fixed nucleus. This is the electron. So I have a fixed nucleus, electron, fixed nucleus, electron, and so on. So when I put these two regions together, in the N material, I have an excess of free electrons that can move around. In the p-type, I have an excess of holes that can move around. Now when I put these two regions together, there's a process that occurs. Since I have a lot of electrons in the n-type, these electrons can diffuse. Now by diffuse, think of it as like dropping a drop of black ink into a clear glass of water. That drop, as it goes into the water, it's going to diffuse out and eventually fill the whole glass. Now a similar thing happens in this PN interface area, but there's something that stops the diffusion, and let's talk about that. Now here I have an electron. Now this electron can move around. It can diffuse over to this location. And when that happens, that electron fills a void in this atom on the left side, in the p-type material. And so it gets locked in to the structure, and it's not free to move around anymore. So I will erase this electron. And when that happens, this region in the p-type material becomes minus because it has gained an electron. But the electron has left the location on this structure in the n-type material. So this region becomes positive. And the same thing can happen at this electron here. It can move over and go into this whole location. And when that happens, we call that recombining. And what happens is these are no longer free charge carriers to move around. And this region again becomes negative because it has gained an electron. And this region is positive because it has lost an electron. And the same thing can happen down here. This electron, let me erase it here. As this electron moves over, combines with this hole, we gain a positive or a negative charge here and a positive charge here. So this region in here becomes devoid of charge carriers. And we call this region a depletion region. So this region here is called a depletion region because it's depleted of mobile charges. They have recombined in the structure. Now, observe what happens. Since I have positive on this side and negative over here, inside this depletion region, there's an electric field that points in this direction. Now, recall that an electric field is a measure of force on a small positive charge in this region. So what's going to happen is as these holes try to diffuse towards the right, they're going to be pushed away by this electric field. That's going to repel the holes. So the diffusion of the holes into the N-type material gets blocked by this electric field. And similarly with the electrons. Now this electric field will exert a force on the electrons to the right in the opposite direction. So the abundance of electrons at the right in this N material get repelled. They no longer diffuse over into the P region. So what does this mean? Let's do a plot of voltage. Now this region in the P-type to the left of the depletion region is neutral. So if we plot the voltage, it has a constant voltage. And when we encounter this E field, the voltage ramps up. And when we get to this side of the depletion region, the voltage in the inside remains constant. So this built-in voltage relates to this electric field. And once we put this P-type and N-type region together, the electron diffuse over into the P region and create a negative region, and the holes from the P region diffuse over the N region, and it creates a positive region. It sets up an electric field that blocks further diffusion, and this results in a voltage differential in this region, and so there we have a net voltage change here. Now in part 2 we will talk more about this depletion region and how that forms a